In this module, we will be taking a brief look at the main components of the Rolls-Royce Tay engine. Particular attention will be paid to the high and low pressure spools within the engine and their constituent parts. We shall look at the high and low speed gearboxes and their role in powering various aircraft systems. Of these systems, we shall be describing in detail the engine oil system and the two-pump fuel system which supplies the engine. The function of the engine multiplexers will be outlined with regard to their role in supplying engine data to various avionic systems. The individual engine parameters of the primary and secondary pages of the multifunction display system will be explained, and the alternative engine indication unit located. We shall be discussing the air starter motor system and demonstrating the light-up procedure using the controls on the engine start panel. With regard to thrust control, we shall be outlining both manual and automatic control of the thrust levers on the pedestal. We shall demonstrate the operation of the thrust rating panel and discuss its use in the automatic, semi-automatic, or manual control of engine thrust. Finally, we shall look at the various engine malfunctions and how they are indicated to the crew. The procedure for dealing with each malfunction will be detailed. The aircraft is powered by two Rolls-Royce Tay 650-15 turbofan engines, each producing 15,100 pounds of thrust, flat-rated to ISA plus 15 degrees centigrade. The engine design is based upon a modular concept. The 7 engine modules are a low-pressure compressor fan, an intermediate pressure compressor, a high-pressure compressor, a combustion section and high-pressure turbine, a low-pressure turbine, a high-speed gearbox, and finally an intermediate compressor casing. The engine has a two-spool design, one each for the high and low-pressure systems. The low-pressure spool links 3 of the modules we previously looked at, namely the fan, the 3-stage IP compressor, and 3-stage LP turbine. During engine operation, the RPM of the LP spool is designated N1. The HP spool links the 12-stage HP compressor and the 2-stage HP turbine. Its RPM is designated N2. The LP shaft passes through the HP shaft, but each rotates independently of the other. Located on the IP compressor casing are 2 gearboxes, the high-speed gearbox driven by the HP shaft and the low-speed gearbox driven by the LP shaft. The high-speed gearbox is responsible for driving various aircraft system components, namely the hydraulic pumps, fuel pumps, oil pumps, integrated drive generator, fuel flow regulator, and the N2 tacho generator. The air starter motor operates via the high-speed gearbox to drive the HP shaft for engine start. The low-speed gearbox is only responsible for driving the N1 tacho generator and the N1 shaft governor. Fan output is split into 2 airflows by the bypass duct, which starts at the IP compressor. Only 1/4 of the airflow enters the engine core. The remaining 3/4 is directed around it. Air is compressed by the IP and HP compressors. Some of this air exits through 2 bleed air ducts at the 7th and 12th stages of the HP compressor. This is used for aircraft services and anti-icing. Beyond the HP compressor, air enters the combustion section. This consists of 10 combustion chambers installed in an annular casing. The chambers are interconnected to allow flame spreading between them. The fuel-air mixture in the combustion chambers is ignited by 2 igniter plugs located in chambers 4 and 8. Hot gases from the combustion chambers drive the HP and LP turbines and then pass through a 12-lobe mixer unit. This mixes the hot exhaust gases with the cool bypass air, thus lowering the exhaust gas temperature and its noise level. Finally, the engine gases are propelled through an engine exhaust nozzle, which increases the jet velocity and therefore engine thrust. The exhaust nozzle also houses a two-door thrust reverser unit, which when deployed deflects the exhaust flow vertically and forward. Engine limit exceedances are detected by MFDS and subsequently signaled to the FWC. If appropriate, the FWC then returns a signal to MFDS to display the associated message and procedure. We shall continue by looking at some of the engine systems driven by the high-speed gearbox. First, the oil system. Engine oil is stored in an oil tank on the lower left side of the engine. The oil used is Aero Shell Turbine Oil 390 or other approved oils. The oil system is completely self-contained. Oil is pumped from the oil tank by means of a single pressure pump driven by the high-speed gearbox. On the output side of the pump is a cooler unit which uses fuel to cool both engine and IDG oil. Oil which is too thick to pass through the cooler unit is diverted around it by means of a bypass valve. From the cooler, oil passes through a temperature sensor which outputs data to the MFDS and FWC. Before being distributed to the engine bearings and gearboxes, the cooled oil passes through a pressure filter. Once the oil has circulated through the engine bearings and gearboxes, 5 scavenge pumps collect the oil and return it to the oil tank. The returning oil passes through a filter, magnetic chip detector, and deaerator before passing into the oil tank. We shall continue by discussing the engine fuel system. Fuel from the collector tanks enters the engine's low-pressure fuel pump. This pump is driven by the high-speed gearbox. From the LP fuel pump, fuel passes through the engine and IDG oil coolers, where its temperature is increased by heat exchange with the oil. This helps to prevent ice formation in the fuel filter. On the output side of the oil cooler, the fuel passes through a series of sensors which measure temperature, pressure, and flow. These sensors feed data to the FWC and MFDS displays via the engine multiplexer. All fuel passes through a filter unit. Located on the filter housing is a differential pressure switch which senses the fuel flow pressure on each side of the filter. If the filter becomes blocked, this switch closes, causing a flight deck alert. From the filter, fuel passes into the high-pressure fuel pump. This is also driven by the high-speed gearbox. The output of the HP fuel pump is governed by a fuel flow regulator. This unit controls the delivery of fuel to the combustion chambers. The regulator meters fuel according to thrust lever position, N2, and HP compressor inlet and outlet pressures. The regulator splits the fuel into 2 flows. One flow goes via the N1 governor to the shutoff valve. The N1 governor prevents N1 exceeding its maximum RPM by limiting the HP pump output. The second flow from the regulator passes directly to the shutoff valve. This valve controls the entry of the fuel to the nozzles in the combustion liners. The shutoff valve for each engine is operated by its respective fuel lever located on the thrust lever pedestal in the cockpit. Moving on, we shall now look at the engine starter system. The aircraft has an air-operated starter motor consisting of a single-stage turbine which drives an output shaft. The starter motor can receive air from one of 3 sources: the APU, an external source, or cross-bleed air from the opposite engine if it is running. Source air must pass through a control valve before entering the starter motor. The valve is normally closed. During engine start, the valve is opened via a control on the flight deck. We shall deal with this process in greater detail during the discussion of engine operation. Air passes through the open control valve and turns the starter motor turbine. This in turn produces rotation of the starter motor output shaft. The output shaft from the starter motor drives the HP spool via the high-speed gearbox. This in turn causes rotation of the LP spool, which is essential for engine start. Continuing our description of the power plant, we shall now discuss engine parameter indication. Each engine transmits data regarding certain parameters to a dual-channel engine multiplexer, or EMUX. The dual channel allows cross-referencing of data for accuracy. The EMUX units send engine data to the Automatic Flight Control Augmentation System, or AFCAS, the Flight Warning Computer, and the Multifunction Display System.
If one of the channels on EMUX fails, a flight deck alert indicates this fault.
Both MFDUs display engine parameters automatically after power-up. The left MFDU shows the primary page, and the right MFDU shows the secondary page. The primary page displays the engine pressure ratio, or EPR, turbine gas temperature, or TGT, N1, and N2. The selected thrust rating and its associated parameters is also shown, along with the total air temperature and static air temperature. The secondary page on the right-hand MFDU shows oil pressure and temperature. Oil quantity is also shown prior to engine start or 5 minutes after engine shutdown. Vibration parameters for each engine are indicated, as are the fuel temperature, fuel flow, and fuel used. Should the MFDS system become faulty, the standby engine indicator can be switched on to give the EPR, TGT, N1, and N2 values. The standby engine indicator is connected directly to the engines. Finally, in this section on engine description, we shall look briefly at those panels and controls associated with engine management on the flight deck. First, the engine start panel located on the overhead panel. This houses the engine start push button, the engine start selector switch, the 4-position ignition selector, and the engine vibration push button. Located to the rear of the pedestal is the thrust rating panel with its 5 thrust rating push buttons and rotary temperature manual EPR selector. The pedestal houses the thrust levers with their take-off go-around triggers, the reverse thrust levers, and the fuel levers. The auto throttle disconnect buttons are also located here. Finally, located on the flight mode panel is the push button to engage the auto throttle system. This panel and the others we have just mentioned will be discussed in more detail in the operations section which now follows. In this section on engine operation, we shall initially look in greater detail at engine indication on the MFDS. Engine parameters are displayed upon left and right MFDU screens immediately upon power-up. The current value for any engine parameter is indicated by a moving tape, one for each engine. The primary page indications have calibrated scales relevant to the particular parameter being measured. Normal operational values are indicated by a green tape. If normal operational values are exceeded, the tape color changes to amber. This is accompanied by a flight deck alert. If a parameter reaches an over-limit value, the color of the tape changes to red and an alert of the appropriate level will sound on the flight deck. In addition to the tape color changing when limits are exceeded, there is also a numeric indication of the over-limit value in amber or red. Should a fault develop in the sensor for a particular parameter, an amber inoperative replaces the tape display, or a line of dashes replaces any numeric values. We shall now look at each of the engine indications in turn, starting with the EPA on the primary page. Current values of engine thrust are indicated by the moving EPA tapes. This value is also shown by a numerical readout at the top of the scale. The tapes and numbers are always green. Other EPA indications will be discussed during the operations and malfunction sections.
The turbine gas temperature scale has an amber limit mark. This mark is not visible prior to engine start and only appears when the engine reaches idle. The amber mark disappears during engine start and reverse thrust.
The red limit mark repositions during engine start and reverse thrust. We shall discuss both red and amber limits in greater detail in the malfunction section.
The N1 column has a red limit marker. This marker is fixed at 95.5% and does not reposition.
The amber limit on the N2 column disappears during engine start and reverse thrust. During reverse thrust, the red limitation marker repositions. If the primary parameters cannot be displayed on the MFDU because of a fault, they can be shown on the standby engine indicator in the center instrument panel. When switched on, the standby engine indicator shows EPA, TGT, N1 and N2. We shall continue our brief review of engine indications by looking at the secondary page parameters on the right MFDU. If either tape falls below the amber limit marker, the tape turns amber. The amber marker position varies with N2 and disappears when N2 is below idle. The red oil pressure limit varies with N2 and moves to the minimum oil pressure index when N2 is below idle. The oil temperature column shows two amber limitations, one for maximum temperature and one for minimum. The column also shows a red over temperature limit.
If oil quantity drops below the upper limit of the oil quantity range, the green tape for that engine turns amber. Please note that oil quantity is only shown on the MFDU before engine start or at least 5 minutes after shutdown of both engines on the ground, and the oil pressure, temperature and fuel flow indications should be at 0.
The engine vibration indicator has 4 tape displays. The inner 2 tapes show N2 vibration and the outer tapes show vibration within the N1 spool. If vibration in either of the spools exceeds a threshold limit, the tape for that spool turns amber. The fuel display shows fuel flow in kilograms per hour and the fuel used in kilograms. The fuel used value is reset to 0 during engine start on the ground. Fuel temperature is indicated in green when the temperature is within limits, but the numerals change to amber or red if over-temperature occurs. The MFDS control panel provides control over the display of engine parameters on the 2 MFDUs. The engine push button on the MFDS control panel allows the secondary page engine parameters to be switched on or off. Display the secondary page engine parameters on the right MFDU. When the engine push button is pressed, a horizontal bar is illuminated on the push button. At the same time, the secondary engine parameters are displayed on the right MFDU. Pressing the push button again would remove the engine indications and the push button illumination would disappear. Pressing the transfer button allows pages from the left MFDU to be displayed on the right MFDU or vice versa. Please note that if the left MFDU fails, the primary page is automatically displayed on the right MFDU. We shall begin our review of engine operations by looking at the engine start and ignition procedure. This is accomplished via the engine start panel on the overhead panel.
The ignition selector knob on the engine start panel has 4 positions: continuous 1, normal, continuous 2, and relight. With the ignition selector set to normal, both of the igniters are activated when an engine failure is sensed. This is the normal operating position. In the continuous 1 position, the number 1 igniter is used. In the continuous 2 position, the number 2 igniter is used, as shown here. For the igniters to operate in the normal or continuous selections, the fuel levers must be open. With the igniter selector set to relight, both igniters are activated irrespective of the start push button and fuel lever positions. We shall continue by demonstrating engine starting. The first step is to select the normal ignition position. Select the normal ignition selector position.
The starter system is electrically armed by pressing the start push button on the engine start panel. Energize the starter system. An on indication on the push button shows that electrical power is available to the starter system. The engine start selector switch activates the air starter motor for whichever engine has been selected. The switch is self-centering. Activate the starter motor for engine 2. When the engine start selector is operated, the control valve to the starter motor is opened. This allows bleed air to enter the starter motor and drive the HP spool.
Rotation of the HP spool creates airflow through the engine, which causes the LP spool to rotate. HP spool rotation, N2, should be monitored until it reaches a minimum value of at least 15%. N1 must also show an indication of rotation. At minimum 15% N2, the appropriate fuel lever should be moved to the open position to initiate light-up. Please note that the fuel lever has to be unlatched before it can be moved.
Move the number 2 engine fuel lever to open. With the fuel lever selected open, the HP fuel shutoff valve to that engine opens, thus allowing fuel to the combustion chamber nozzles. At the same time, the igniter is activated. Light-up should occur within 10 seconds.
If light-up does not occur, the fuel lever should be shut. The starter can be cranked a maximum of 3 times with up to 30 seconds for each crank, but should then be left to cool for 15 minutes.
When N2 reaches 43%, the control valve to the starter motor automatically shuts and the ignition is cut off.
Finally, after both engines are started, the start push button should be switched off. This also results in the secondary engine parameters disappearing from the right MFDU.
We shall continue with a review of thrust control. Thrust for the engines is controlled through 2 thrust levers located on the pedestal. Each engine thrust lever is connected to its corresponding fuel flow regulator in the engine fuel system. Operation of the thrust levers can be done manually or automatically via the auto throttle system. The auto throttle system, or ATS, is part of AFCAS. This automatically sets the thrust lever position according to current speed or thrust requirements.
On the ground before takeoff, ATS is armed by pressing the AT Engage push button at the FMP. When armed, the push button shows a green horizontal bar. Then, upon pulling the toggle triggers on the thrust levers, ATS engages. Please note the FMA AT Engage status is now shown. Also note ATS automatically engages in flight during an aircraft overspeed condition or during alpha floor protection, or if the toggle triggers are pulled for a go-around. During flight, the AT is manually engaged using the FMP AT Engage push button.
Located in each thrust lever handle is an AT Disengage button. Pressing either of these reinstates manual control of the throttle levers. The reverse thrust levers are located on the forward side of the thrust levers. The reverse thrust levers cannot be operated if the thrust levers are in a forward position. The thrust levers must be in the idle position before the thrust reverse levers can be operated, and they can only be operated if the aircraft is on the ground. Move the thrust levers to the idle position. As soon as the thrust levers are at idle, reverse thrust can be selected by pulling the reverse thrust levers upwards. This will deploy the thrust reverser buckets. Deploy the thrust reversers. When the thrust reverse levers are pulled, they initially move to a detent position. This is the reverse idle position. It is at this stage that the thrust reverse buckets are deployed. When the thrust reversers are deployed, green R symbols appear on either side of the EPA scale to indicate their deployment.
Lifting the thrust reverse levers beyond the idle detent allows progressive application of reverse thrust power to a detented normal maximum position. In an emergency, it is possible to use a higher level of reverse thrust by pulling the levers up beyond the normal maximum position. The emergency maximum position is spring-loaded, but does not return to their original position when released.
The reversers are stowed by pushing the thrust reverse levers fully down. We have already indicated that the auto throttle system is part of AFCAS. The thrust rating panel on the pedestal also provides inputs for automatic thrust management. 5 push buttons on this panel allow thrust ratings to be selected for different phases of flights. These are
Takeoff, go around, flexible, climb,
cruise, and maximum continuous. When a button is pressed, AFCAS computes a suitable maximum thrust value for the ambient conditions and the selected thrust rating. Thrust values are indicated by the engine pressure ratio, or EPA. EPA is the ratio of fan inlet pressure to fan duct pressure. The actual EPA value and the selected thrust rating are displayed on the left MFDU above the EPA column. Please note that TOGA is the default selection upon power-up. 2 white wedges show the calculated maximum thrust values on the EPA scale. This upper limit should not be exceeded. AFCAS, via the auto throttle system, will control thrust lever position so as not to exceed this maximum thrust value. If TOGA is the selected thrust rating, then AFCAS computes the maximum EPA value for the ambient conditions. This maximum level of thrust will be employed when the TOGA triggers are pulled. Takeoff occurs in the shortest possible runway distance. If flexible mode is selected for takeoff, it is possible to get AFCAS to compute a lower thrust value. This means that maximum thrust is not used during takeoff, thus reducing engine wear.
When flexible is selected, it appears with the current ambient temperature and the maximum EPA value for that temperature. Blue lazy T's also appear, superimposed over the white wedges. The lazy T's represent target EPA values for the flexible mode.
Located on the thrust rating panel is the temperature or manual EPA selector knob. The outer knob is a 2-position selector for either temperature or manual EPA. The inner knob allows adjustment of temperature or EPA values depending on the switch position. In flexible mode, an assumed ambient temperature is dialed in using this knob. Dial in a new assumed ambient temperature and observe the change on the MFDU. AFCAS uses the assumed temperature to compute a new target EPA value, which is lower than the actual maximum thrust value. The new value is displayed, and the lazy T's reposition to show the new EPA targets for the ATS during takeoff. For takeoff with flexible or toga selected, and the AT push button on the flight mode panel engaged, pulling the toga triggers activates the ATS. The throttle levers move forward to produce the maximum or target EPA values. Please note that during takeoff, the ATS is automatically declutched at approximately 80 knots. This is for safety purposes to facilitate an aborted takeoff. When it is declutched, this is indicated by D symbols on either side of the EPA scale. ATS automatically re-engages at 400 feet. If AFCAS fails, EPA limiting values can be manually entered and displayed on the left MFDU. This is done using the manual EPA position on the temperature or manual EPR selector. Please note that the thrust rating and digital EPA value disappears if AFCAS fails. The white wedges also vanish.
Manual EPR can also be displayed if only ATS fails or if ATS is switched off at the flight augmentation panel. Actual EPR numerical value should remain displayed if FCCs fail. Only target and thrust rating are removed.
Set the selector switch for a manual EPA input. When manual EPA is selected, this is indicated in the thrust rating position above the EPA scale. Also shown is a default EPA limit value. The blue lazy T's change to white and show the EPA limit value. The inner knob on the temperature manual EPA selector is rotated in either direction to increase or decrease the EPA limit value. Reference tables must be used to provide an appropriate EPA value. Once the new EPA limit value has been selected, the lazy T's reposition to show the target value. Manual control of thrust should be kept within this indicated limit value. We shall begin our review of engine malfunctions by looking at engine failure. A straight flameout is indicated by a rapid decrease in EPA, TGT and N2 values. The left MFDU identifies the fault, and the right MFDU gives the procedure for an engine failure. Consult the QRH to confirm the procedures and for any additional information regarding this alert. Also shown is the alert inhibitions table for this procedure as shown in the AOM. The light on the fuel lever of the affected engine also comes on. The fuel lever light is illuminated for any level 3 engine alerts which may require the engine being shut down.
If the ignition selector knob is in the norm position, a relight will be automatically attempted. If the engine failure is caused by a flameout due to, e.g., fuel starvation, extreme turbulence, or icing, a manual relight should be considered after the cause has cleared.
If there is no immediate engine relight, the fuel lever of the affected engine should be shut and the ignition selector rotated to the normal position. ATS can then be re-engaged by positioning the thrust lever of the inoperative engine beside that of the live engine. Please note the full relight procedure. With one engine inoperative, the QRH should be consulted for details of the single engine procedure.
A Level 2 alert occurs if a miscompare between two MFDS calculated EPR values for the same engine arises. The relevant caution message will also appear. In this situation, the standby engine indicator should be switched on to provide accurate EPR values.
Note the alert inhibition table for this procedure. Our next consideration will be a high turbine gas temperature in one of the engines. A level 2 alert occurs on the flight deck.
In addition to identifying the fault and providing the appropriate procedures, the MFDS also shows an amber tape indication for the affected engine parameter. During takeoff, TGT may be above the amber line without an alert and tape color change.
The stated procedure is to retard the appropriate thrust lever and monitor TGT. Assume that ATS is disengaged and retard the thrust lever. If retarding the thrust lever reduces TGT to an acceptable level, the engine may be operated at this lower thrust setting. However, if reduced thrust does not control TGT, then it is necessary to close the fuel lever to the affected engine. Close the fuel lever to the affected engine. Moving the fuel lever to shut closes the HP fuel shut-off valve, thus starving the engine of fuel. With the engine shut down in this way, the single engine procedure should be followed. If TGT reaches an over-limit value, a level 3 alert occurs. The MFDU screens supply the relevant alert and procedure messages. A red tape and digital display indication occurs on the affected engine's TGT display. The measures for dealing with a TGT over limit are similar to the procedures for the TGT high scenario. However, a TGT over limit can only be tolerated for a very short period of time before the fuel lever should be closed.
During flexible, toga, or manual thrust rating modes, TGT may be transient above the amber limit for up to 5 minutes, providing the red limit is not exceeded. TGT values may also be transient above the red limit for a maximum of 20 seconds, provided the maximum transient temperature is not exceeded. Note, when after a takeoff climb is selected, the TGT may exceed the amber limit for 20 seconds.
The QRH should be consulted for the specific and any additional procedures regarding TGT alerts. Also shown is the appropriate alert inhibition table. Moving on, we shall now discuss N1 and N2 alerts. Should N1 and N2 values become high and exceed normal operating limits, a level 2 alert occurs. We shall describe a high N2 alert, but the same procedure applies to a high N1 value. Check the MFDU messages and determine the extent of the problem from the tape indicators on either the N1 or N2 column. The procedure is the same as for a high TGT situation. The thrust lever of the affected engine should be retarded and the N2 value monitored. If N2 is brought within limits, continued operation at a lower thrust setting is permitted. If retarding the affected engine's thrust lever does not reduce the high N2 values, the fuel lever should be closed and the single engine procedure applied. If N2 or N1 develops an overspeed condition, a level 3 alert occurs. Follow the indicated procedure. Retard the thrust lever of the affected engine, and if this does not quickly restore normal values, close the fuel lever and apply the single engine procedure.
If flexible or toga modes are being used, N2 values may be transient above the amber limit for up to 5 minutes, provided the red mark is not exceeded. Transient values above the red limit are permitted for a period of up to 20 seconds, provided the maximum transient RPM isn't exceeded. The N1 tape will be amber during these periods.
The QRH should be checked for the specific and any additional procedures pertaining to N1 or N2 high or overspeed values. Please note the alert inhibitions. Moving on to the secondary page indications, we shall now consider the procedure if low oil pressure is detected. A Level 2 alert results. In addition to the alert and procedure messages, the indicator tape for the affected engine will have dropped below the amber limit and will have changed from green to amber.
The procedure states that the thrust lever of the affected engine should be retarded. This may bring the oil pressure back to within normal operating limits.
If the oil pressure for the affected engine can only be returned to normal by retarding its thrust to idle, single-engine procedure should be considered.
If oil pressure in an engine drops below the red limit marker, a Level 3 alert ensues with appropriate messages on the MFDS.
If the oil pressure indication shows a value below the red limit mark, the thrust lever of the affected engine should be reduced to idle. If the condition persists, the fuel lever for that engine should be shut and the single-engine procedure adopted. The QRH lists the appropriate procedures for both low oil pressure and oil pressure limit being exceeded. We shall now consider oil temperature alerts. A temperature bulb on the output side of the combined engine and IDG oil cooler provides oil temperature data to the engine multiplexers. If a high oil temperature is detected, a Level 1 alert results. An amber tape condition is shown on the indicator for the affected engine. Please note the procedure. A high oil temperature may be reduced by increasing the flow of fuel through the engine and IDG oil cooler unit. This is accomplished by advancing the thrust lever of the affected engine. If the oil temperature exceeds the red limit mark, a Level 3 alert results. Once again, note the alert messages and procedure. An oil over temperature condition necessitates the thrust lever for the affected engine being retarded to the idle position and its fuel lever shut. Single-engine procedure should then be applied. Consult the QRH for full procedural information. Also shown are the alert inhibitions as illustrated in the AOM. A low engine oil quantity results in a Level 1 alert. Please note that oil quantity can only be measured accurately before engine start or 5 minutes after engine shutdown. If refilling is not possible, check the MEL for flight time restrictions. Please note the procedures for the oil system alerts as shown in the QRH. Moving on, malfunctions in the engine fuel system will now be described. If the fuel temperature sensor detects a high fuel temperature, this results in a Level 1 alert. Having identified the alert and the procedure from the MFDS, check the appropriate fuel temperature display. A high temperature is indicated by amber numerals.
A problem cause of high fuel temperature is a high IDG load combined with a low fuel flow through the IDG cooler. The IDG load can be reduced by switching off electrical power in the galley, since this is the prime user of electrical power.
Fuel flow through the cooler is increased by advancing the thrust lever of the affected engine. Shutting the galley power off and increasing the fuel flow should reduce fuel temperature. If fuel temperature is not controlled and continues to rise to an over-temperature condition, a Level 3 alert occurs. The fuel temperature indicator changes from amber to red numerals, and the appropriate procedure is displayed on the right MFDU. The QRH echoes the procedure shown on the MFDS and should be consulted for any additional information. Please note that the generator should be switched on before approach in order to retain auto-land system capability. A Level 1 alert occurs if the fuel filter becomes clogged. The most probable cause of this problem is the presence of ice in the filter. The left MFDU identifies the location of the fault, in this case number 1 engine. The procedure states that the fuel temperature should be checked to verify if it is below zero. Retarding the thrust lever of the affected engine to idle reduces the flow of fuel through the engine oil cooler. This should result in an increase in the fuel temperature. Once the temperature rises, the thrust lever can be readjusted. Check the QRH for full procedures. Please note the alert inhibitions as shown in the AOM. If low fuel pressure is detected in an engine, a level 2 alert results.
If low fuel pressure is detected in an engine, a level 2 alert results. Once again, the MFDS identifies and states the procedure for this particular alert.
The fuel pumps should be checked to see if they are on, and then the crossfeed button should be pressed to initiate crossfeed. Here we see a review of the procedure as shown in the QRH. Please note the alert inhibitions for this procedure. Should the thrust reverser become unlocked on the ground or accidentally deployed during flight, a level 2 alert occurs. The stated response is to apply the reverser unlocked procedure. The reverser unlocked procedure is detailed in the QRH. Please note the alert inhibitions from the AOM. Next in our discussion of alerts, we shall look at excessive engine vibration. If vibration in the engine spools exceeds normal limits, a level 1 alert results. The tape indicators for the engine that is vibrating turn amber, and amber numerals show the level above the threshold in inches per second. The vibration push button on the engine start panel shows an amber high indication. This button should be pressed to ascertain if the high vibration indication is due to sensor error. It does this by switching between the two sensors which detect engine vibration. Switch engine vibration sensors. Pushing the vibration push button results in the amber indication disappearing and a white alternate text appearing. The second sensor which detects engine vibration now sends data to the indication system. If the vibration tape indicators return to normal values, then the alert was due to inaccurate sensor data from one of the two sensors. If the alert persists, retard the thrust lever of the affected engine to idle. Note the alert inhibition table for this procedure. We shall now look at engine start faults. If the control valve of the starter motor remains in the open position after engine start, or if there is a starter cutout fault, a level 2 alert occurs. The start push button on the engine start panel shows an amber fault indication. Confirm the nature of the alert from the MFDS and consult the QRH for the necessary procedure. Note also the interrupted start procedure. By pressing the start push button to the off position, electrical power to the starter system is cut off. This should lead to the control valve shutting. If the aircraft is on the ground and the alert persists, all bleed air sources should be switched off. This is to prevent damage to the air starter motor. The fuel lever of the affected engine should also be closed.
Please note the procedures for these additional engine start faults. No flight deck alert occurs, and no high TGT readings are displayed for any of the problems shown.
In concluding this section on abnormal procedures, we shall look at two malfunctions which necessitate emergency procedures. The first is an engine overheat which results in a level 3 alert. Note the MFDS messages for this situation. The stated procedure is to retard the thrust lever of the affected engine to idle and shut its fuel lever. The QRH reviews the necessary procedure. Please note that this alert is not inhibited. Finally, note the procedure for a double engine flameout. This procedure is only described in the QRH since if both engines fail, no electrical power is available for the MFDS. In this module, we have noted that the aircraft is powered by two Rolls-Royce Tay 650-15 engines, each producing 15,100 pounds of thrust, flat-rated to ISA plus 15 degrees centigrade. The engine is of a two-spool design. The low-pressure spool, which consists of a low-pressure fan, intermediate compressor, and low-pressure turbine. The RPM of this spool is designated N1. The high-pressure spool comprises a 12-stage HP compressor and an HP turbine. Its RPM is designated N2. We noted that the low-pressure spool drives the low-speed gearbox. This gearbox drives the N1 tacho generator and N1 shaft governor. The high-pressure spool drives the high-speed gearbox. The high-speed gearbox powers the hydraulic pumps, fuel pumps, oil pumps, IDG, fuel flow regulator, and N2 tacho generator. The air starter motor also operates via the high-speed gearbox. A bypass duct splits engine airflow by a 3-to-1 ratio, with the majority going around the engine core. We described how the cooler bypass air is mixed with the hot exhaust gases to reduce engine noise. We noted that the jet nozzle houses a two-door thrust reverser, and that the thrust reversers are deployed by means of the reverse thrust levers on the pedestal. We identified the main components of the engine oil system and described their function. The two-pump fuel system was also discussed, and it was noted that fuel flow to the combustion chambers is metered by the fuel flow regulator. It was stated that the HP fuel shut-off valve is opened or closed by the fuel lever on the pedestal. We identified and described the key features of the air starter motor system, and the engine light-up procedure was demonstrated using the controls on the engine start panel. The role of the dual-channel engine multiplexers in supplying the MFDS, FWC, and AFCAS was outlined, and we described in detail each of the parameters shown on the MFDS. The standby engine indicator was located and identified. We noted that the thrust levers can be controlled manually or by the auto throttle system. The AT engage push button on the flight mode panel and the AT disengage button on the thrust levers were located and identified. The turbo triggers were located and their function in initiating the auto throttle system explained. We saw that the thrust levers have to be in the idle position before reverse thrust can be selected. It was stated that the reverse thrust levers have 4 positions: stowed, reverse idle, normal maximum, and one for emergency maximum reverse thrust. The function of the thrust rating panel in setting maximum or target EPA values was described, and the indication of the selected thrust ratings on the MFDS demonstrated. We saw that selecting flexible mode and dialing in an assumed temperature allowed lower thrust values to be used for takeoff. This reduces engine wear. It was also stated that if AFCAS fails, EPA limits can be entered via the temperature manual EPA knob.